Okay. I don't have these covered up. So I would love for you to kind of do a textbook walkthrough and fill out the things that you see. Um, so if you notice, we're starting on page 106 and going through to page 111 on the textbook. Okay. So we are going to cover intro to chapter 7, 7.1, 7.2, 7.3, and 7.4. I've covered up with Newton because I kind of want you to come up with some of these on your own. When we do them in class, I'm going to ask you to take a couple minutes and list these to the left side. That means you should be reading through 7.1. Just do a quick skim. What are the key ideas? What are the things that it mentions? Look at the pictures. You should do a textbook walkthrough. That is what this is called. Okay, I'm going to go ahead and get started. I'm going to talk about the intro and review. All of this, Newton's first, second, and third law, all kind of coexist with each other. So the idea here, we're going to play around with the idea of inertia. We're going to deal with force, mass, and acceleration and their relationship. So the first thing that they mention is they tell this story about this like kayaker, okay? Or like when you lean too far, you tend to fall over. So the biggest idea in this whole unit is the idea that, for example, when you run, if you are running, your foot on the ground, yay, you're running. Okay, as you run, this is a terrible runner. As you run through the ground, the reason you are able to physically run is as your foot pushes down on the ground, there's a sense of resistance. There's this traction or resistance. The track is made especially to increase that friction, right? The ground pushes back on your foot. If we were to lift you in midair and remove the ground completely, you have nothing to push on. So there's no longer any force. So if we draw this 2 times, here's you, here's your force downward, here's the force of the ground pushing back on your foot, allowing you to propel yourself forward. If I take you out into space and drop you out of my spaceship, here you are running in space. Wait a minute. There's nothing to create traction. There's no reaction. So you have nothing to push on. So there are no forces. You are just floating. Okay. That takes us right into forces and interaction. So there's always a mutual pair. To a force. In order to have a force, one direction, there's got to be a response another direction. Okay? There's got to be something to react with it. Otherwise, there is no force. For example, if you punch the air, this is you punching nothing, right? You're punching the air. If there's nothing to hit, you've applied no force. You're just swinging your arms around like a crazy person. Okay? So there must be a mutual pair to a force. In order for there to be a force, must be a mutual pair to a force. Okay, they always occur in pairs. Which takes us directly into Newton's second law. The law says for every action, there is an equal and opposite reaction. This is important, all right? So I have a couple samples that I'm going to talk to you about, but the first one would be the running situation, the action force running. I'm going to give here The action force is pushing on ground. Reaction would be ground pushing on foot. Okay, that's our running force. What about, I like another one. There's a couple more examples in the book. On page 107, there's some nice pictures. The next one is a dude. So here you're talking to this cute lady, and you're looking real cool. You're leaning. You got the lean mastered. You are just like leaning up against that wall, right? Looking super cool. As you lean, you are pressing on the wall. Now, if you make an epic mistake, and as you lean, you realize you're actually leaning on something with wheels, you see the direct action of your force. Push on it, and the cart moves, and then you fall over and embarrass yourself. If you actually are leaning on a wall, the wall does not move. Why does the wall not move? As you push on the wall returns that push on you. All right? So the action would be you pushing on the wall, you on wall. The reaction is wall on you. And you don't look foolish in front of your lady friend. Okay, third example. And this one you can kind of feel. If you've ever hammered something, like there's a distinct feel in your hammer when you strike the nail. So as you're holding this, right? Here's your hand. This is you holding a hammer. As you strike the nail, this is the force of the hammer, right? And then this is the force of the nail. You feel the nail because it vibrates all the way back into your hand, all right? Otherwise, if you just swing a hammer up and down, you're not hitting anything. You're not applying a force. You're just spinning a hammer. You could tomahawk the hammer, but that's still not applying a force to anything. Okay? So hammer on nail. The reason why the nail responds is because it received the force from the hammer and reacted. Nail on hammer. And it moves at a different acceleration. So this is where we're going to get into identifying action-reaction pairs and looking at how they have an effect on movement, right? Because usually the mass of the hammer, I'm going to throw this out here. Mass of hammer is big, mass of nail is small. This is where you're going to see Newton's second law come into play. So action-reaction forces. Let's move my picture out of the way. Okay, so I'm going to do some more samples. We did a bunch up here, but we'll do a couple more just because we like pictures. Car on the road. As you guys learn how to drive, you're realizing on snowy days, or if you haven't yet, you will realize on snowy, slick days, why we have, apparently we don't have snow days, but why we sometimes have snow days is because you can't get traction. As your wheels push down on the road, the reaction force is the road pushing back on the wheel. That's what allows you to move forward. That traction is what we usually call it. By pushing down, the action force is wheels on road, and the reaction force is road on wheels. If you're on ice or in mud, that is why your wheels just spin, and the reaction force is, oh, hey, look at that, is the spinning of mud behind you. That is your reaction force because you are not getting that solid traction of forward. Like instead, you're pushing down, and the mud's reacting and shooting backwards. A rocket, purple. Here's my rocket, right? And it launches. Woo! Okay, as the fuel, action is fuel. pushing on rocket. Reaction is rocket pushing. Rocket push. Oh, whoops! I flip-flopped this. Fuel pushing rocket, rocking, pushing fuel. Usually these would be flipped. So if it releases fuel or the gas, fuel or gas, it pushes out against the ground, and in response, that creates a reaction causing the fuel to push the rocket up. Okay, this is where things get weird. Falling objects. Falling objects is probably the most complicated part. When we're dealing with falling objects, we are understanding that there's a building. The object is falling towards the earth. You will all know to label this force of gravity. What the heck is the reaction force? The reaction force, all objects actually have a gravitational pull. And the ball is actually pulling the earth towards it. Force of ball. Oops. Now, the catch is the ball doesn't have a lot of force to apply. So that tiny force that the ball is pulling doesn't really cause this to move at all. Does not move because it's not strong enough to actually pull it, while the earth is large enough and it can pull it. So that would be looking like, here's the dot, here's this giant earth. This is being pulled down by the force of gravity. This is being pulled up by the force of the speck. Okay? The speck can't apply enough force. That arrow is not big enough to cause this movement, this mass to move. So what if you have really big and really small masses, but things do move? This is my favorite for real life stuff. If you look at something like a cannon or a gun, I'm going to do a cannon because it's easier. Here's my cannon. Right? And here's my fuse. Again, I'm going to erase my earth because I'm running out of room. Okay. See my fabulous cannon? It has a really big mass. Big. Ow. Then I have this cannonball. Good. It has a relatively small mass. Okay? We have learned if the exact same force is applied, F is applied. If I have a big mass, in order to get these to balance out, if I have a big mass, I'm going to have a small acceleration. If I have a little mass, I'm going to have a big acceleration. That's the only way they balance out, and this is often called your recoil. Or your kickback in a gun. So it's that feeling you get as this will roll back just a little bit. Well, this will launch if this is my acceleration and my acceleration if the force is the same. Okay? So that's why you get some sort of reaction. Okay? When you push a ball, towards the hoop, you feel the ball in your hand. You feel that pressure, but it doesn't have as much kickback, but you do feel it. Okay, the last thing I want to discuss is lift. So, when we're dealing, this is a complicated one, but when we're dealing with lift, wings and other objects, mostly wings and birds, are designed to have this lift capacity. Their lift capacity just means the shape of their wing is curved in order, as the wind blows down, you create this cavity of air as the thing leans up, and that is your reaction. So this is the tilt of your wing action, which causes this pressure to push up, being your reaction. Okay. Practice questions will be posted on the assignment. Here are the practice questions I want you to attempt. Good luck, and check out the next video for the next set of notes. Hope this helped. Feel free